Hello and welcome once again, coming to you not quite live from One Take Studios, where today's topic is going to be synthetic substitution / division. Alright, this is actually one of my favorite topics. I am amazed by this every time I see it as far as how well all the pieces fit together. So I'm going to show you a couple things and show you how it all ties together and throw in a little bit of the remainder theorem while we are at it. Alright, so to begin, we're going to start with the trip down memory lane with direct substitution. This is something you have likely seen before. Direct substitution is along the lines of, I have a function. Alright, so here's my function, x cubed plus x squared minus 19x plus 26. Direct substitution says, if I want to plug in a 3, I'm just going to plug in a 3. And so this becomes 3 cubed plus 3 squared. Again, the 3 is just taking the place of the x. Minus 19 times 3 plus 26. And I plug that all in, I crank through all my calculations, and I get the number 5. So direct substitution is what it sounds like. I'm going to directly take the 3 and plug it right into the function and get my output as a result of that. Okay, great. How does synthetic substitution work? How is this different? Alright, so for synthetic substitution, quite frankly, it sort of appears like it's a miracle. So check this out. What's so miraculous about this? Notice my strange configuration here. I have the number 3 in kind of a partial box. That 3 matches up with this 3 right here. Here we said we're going to plug in the number 3 directly. Well, synthetically, this is the 3 that we want to plug in. What are we plugging it into? Well, instead of using the full polynomial with all of its x's, we are just using the coefficients. This is 1x cubed, so that's a 1. This is 1x squared, so that's a 1. Minus 19x, so that's a minus 19. And my constant value is 26, there's my 26. So using only the coefficients and ignoring the x's entirely, we're going to attempt to do the same thing and get the same outcome that we just did with direct substitution. Here's how this works. You might want to watch. It's a little hard to describe, and you get better with it. Get better at it with practice. Eventually, by the way, you end up loving this entirely. So check it out. The first number is going to drop straight down. So notice I've got a long addition bar here. The first number is just going to drop straight down. I am then going to take my bottom number, 1, times my box number 3. 1 times 3 is 3. That goes in the next available spot. And going down, we're saying that we add. So what is 1 plus 3? 1 plus 3 is 4. That was so much fun. Let's do it again. Bottom number times box number. 4 times 3 is 12. Add these together. That's going to give me negative 7. Bottom number times box number, negative 21. And again, adding as we go down makes... Oh, wait a minute. Haven't I just seen that number someplace else? Hey! Great! That was weird. Why does it even work? Why am I getting the same number here as I did here? So this originally appears to be like it's magic, right? Some sort of witchcraft has just taken place, but I would like to show you that this maybe isn't quite as crazy as it appears on first glance. So direct substitution, synthetic substitution. Hold that thought for me. And what we're going to look at next is actually this dude right here. All right, let's go back to long division for a moment. I do have another video on long division, so I'm not going to be going through this in great detail, but I do need to show you what's here. So long division says, all right, I'm going to make this match with this. That means this is going to have to be x squared. So x squared times x is x cubed. And x squared times minus 3 is minus 3x. And very much like long division in grade school, we're going to subtract what we've got here. And by design, x cubed minus x cubed drops out. This is 1x squared minus negative 3x squared. That actually ends up being plus, so that's a 4x. Oops, that is x squared. I forgot to write the squared. Yikes. X squared. There we go. All right. And then bring down the next number available, or the next term in this case, which is a minus 19x. Again, I would like for this to match with this, so I have x, I'm going to need the 4, and I'm going to need another x to multiply there. So 4x times x is 4x squared, yay, that matches. And 4x times minus 3 is a minus 12x. Again, I wish to subtract everything in that line. The first term drops out. Exciting stuff. 19 minus negative 12. That's like saying plus 12. That's a minus negative. Wow. Minus 7x. And we have one more term to bring down here, so plus 26 one more time through. I need to match. I have an x. I need a minus 7x, so I need my minus 7. Minus 7x, there we go. It matches. Negative 3 times negative 7 is going to be positive. Did I mess my signs up? Hold up, hold up, hold up. Rar, rar. No. Yes. Maybe. Yes, never mind. I'm fine. I'm fine. Okay, here we go. Honestly, this is one of the reasons I really don't like long division. It is so easy to lose track of something. Again, we're subtracting everything in this line here. So negative 7 minus negative 7, poof, gone, disappears. 26 minus 21 is 5. And that is my remainder. And if you remember, we said that remainders for long division with polynomials, we write it kind of like this. Instead of just putting an r with a 5, remainder 5, we take the remainder and we put it over the divisor, x minus 3. And we would say then that this is our answer for this division problem right here, this guy. All right. Why on earth would I show you this? Look again. And look very carefully at what we just did with synthetic substitution. 1, 1, negative 1926. 1, 1, negative 1926. This is the same polynomial. Here we were dividing by x minus 3, and what was in the box? 3. How are these related? Well, what happens if I take x minus 3 and I set it equal to 0? I get x equals 3. So the 3 is what went in the box, coming from our divisor. Oh, did you even see this? This is insane. Are you still looking? Do you see it? Tell me if you see it. I'm going to try green here. Let's see if green makes it better. Look at these numbers here. This is a 1x squared plus 4x minus 7 plus 5 over x minus 3. Look at this, look at this. 1, 1, 4, 4, negative 7, and 5 was the remainder. Guys, this is not just synthetic substitution. At the same time, it is also synthetic division. Weirdly enough, substitution and division kind of work the same way for this. This isn't magic at all. This is just somebody noticed the patterns in long division and said, hey, I can take these patterns and shorten it up. I mean, even if I'm looking at this, 3, 3, 12, 12, 21, 21. All of the signs are reversed, of course, because we are subtracting here, but every piece of this lines up. So this guy right here, that's this guy right here. This is the same thing. Boom. So synthetic substitution is synthetic division. Now, how would I know? How would I know that this is 1x squared? Is there a good reason for that, a way that that works? Well, let's think about this. We divided, we had an x cubed, and we divided by x. When you divide, you're dropping by a power. So, if that was x cubed, that means that this is going to have to be 1x squared. And then this is descending order, so plus 4x minus 7. So that number is my constant, and that number, again, is my remainder. So that's the plus 5 over what I was dividing by x minus 3. Synthetic substitution, synthetic division. Shortcut for long division. I personally am not fond of long division. I really like synthetic division. Alright, so, exciting stuff. Can I always use synthetic? Can I abolish long division for forever? Sadly, no. There is a reason that it exists. You may only use synthetic division when what you are dividing by is a linear binomial. X minus 3 is a linear binomial. Binomial, 2 terms, and linear, this is x to the first power. So if your power is higher than 1, you can't use it. And if you have more than 2 terms, you can't use it. So this has to be power of 1, 2 terms only, what we are dividing by in order to make this happen. Now, to just make everything come full circle for a moment here, check this out. This is my remainder theorem. Okay, let's see if we can make sense out of the remainder theorem. If the polynomial function p of x, That's just the same function that we've been working with this entire time, right? That function. We just keep using the same function over again. So that's p of x. P is just p because it's a polynomial. You could call it f of x if you want. You can call it kind of anything you want. Is divided by x minus a. Divided by x minus a. X minus a. That kind of looks like x minus 3. I bet they're related. And if they are related, that means that 3 is a. Okay, that seems logical. Then what's true? Well, okay, so I'm dividing. And I'm dividing by x minus a, linear binomial. Then the remainder is p of a. That looks an awful lot like, wait for it, direct substitution, where I plugged in the 3, because the 3 is my a, and I got 5. And what is this saying the 5 is? This is my remainder. So absolutely, completely and totally crazy. Think about what this means. Anytime that you have ever plugged a number in to a polynomial, you have found the remainder to a division problem that you didn't even know you were doing. That's kind of insane. So everything here, full circle, all the pieces fit together with this thing. So we've got synthetic substitution, which is like direct substitution, but crazier because it also happens to be synthetic division. Oh, lordy. Okay, so a lot of stuff going on there, a lot of really, really neat connections, and I happen to really like this. So I would like to do one example just to kind of clarify. We're going to get away from all these examples for a moment here and just kind of go with this. All right, so here's a division problem, kind of forgetting that. As with long division, descending order, no gaps. This is our battle cry. If we are using long division or synthetic, we have to look at our lineup. These have to be in descending order. So there we go. These have to be in descending order, and we don't want to have gaps. Like this is x cubed, x squared, x to the first, x to the 0, descending order, nothing missing. Why do I point this out? Because I specifically picked something for us to work on that has a gap in it. I have x to the 4th, I have x cubed, I do not have an x squared term. Uh-oh. I do have an x term and a constant value as well. So if I'm going to use long division, I'm not going to use long division. If I'm going to use synthetic division, this is a linear binomial. I'm going to set it equal to 0 and discover that x equals -2. Why does that matter? Because if you remember, that's the number right there, that goes in the box. So when I go to set up my synthetic division, I'm going to put a -2 in the box. And then I'm using my coefficients. That's 1 x to the 4th plus 8 x cubed. I don't have an x squared term. I must fill in the gap with a 0. Descending order, no gaps. The 0's got to be there. Minus 3x and then plus 6. Again, notice I'm not actually writing any x's here, just the numbers, just the coefficients. And first number comes down, that's a 1. 1 times -2. Bottom number times box number, -2, and add, that makes 6. Bottom times box, that's -12, and add, that's also -12. Bottoms times box, that's 24. See how much faster this is than long division? That's crazy. I'm going to have some bigger numbers here in a second, but still. So 24, because that's 21, and that's going to be -42 plus 6, the positive, so this is going to be -31. Okay, here's your final test. What does this mean? I would advise you to just pause for a moment and see if you can figure out how this represents the answer. Give it a shot and come back to me. Did you try something? I hope you tried something. So remember what we said. This always drops by a power. I've got x to the 4th divided by x. This is going to drop by a power. So this 1 is going to be 1x cubed. Descending order, that means this is plus 6x squared. This is going to be minus 12x, and then plus 21. Right there, that's my constant, because what's the number on the end? Do you remember? That is my remainder. So -31, and that's going to be over what I was dividing by, which was x plus 2. Ladies and gents, that is the answer to my division problem. Okay, bonus question. If I had plugged -2 into this equation, what would I have gotten? -31, because plugging a number in directly gives me the remainder. Thus says my remainder theorem. Why do I even care what the remainder is, quite frankly? Usually I don't, but if I'm looking for factors, I'm looking for things that divide evenly, it's really nice sometimes to identify which things have no remainder or remainder of 0, and that can be very helpful when I'm working on taking things apart. So I hope you enjoy that. I hope you have fun with it. Practice, get good with it, and then you can kind of ignore long division. Yay. All right. Thanks so much. Bye.